To today's session. What was our last session about? What was our last session about? Our means here in auditorium. We did a sample code wherein we tried to implement a model which could predict a next word using LSTM. Yes or no? And based on that, you did another exercise on sentiment analysis. What was the little tweaking in that? Here we did by creating what? Our random vectors as your word embeddings. There you have here used what? Word to vec. Yeah? Yes or no? Okay. And also next word prediction may you predict the entire word. Sentiment classification, you will, what you will do? What did you do for sentiment classification yesterday? What was the application on? Movie reviews. So you reviewed the movie to be good or bad, right? So you understood the sentence, you calculated the context and tried to fix an emotion out of it and decided what sentiment did that feedback hold. Yes or no? Right. Now, post that, I taught you one more important concept. What was it? Attention mechanism. What is attention? What is attention? Forgot. Huh? Yes or no? Forgot? Tell me so that I can remind you. Did you forget what is attention? And then tell. What is attention? What is attention mechanism? What does it help the machine to? No answer. So, okay. So, listen. Till we did LSTM. What was an LSTM? It was an extended recurrent neural network only. Okay. Post that, I taught you about sequence to sequence model. Yes or no? Yes or no? What does a sequence to sequence model do? It converts one sequence of input into another, transforms one sequence of input into another. What are the important components of sequence to sequence model? Encoder, decoder and a context vector. So what you do there is, inside an encoder, you will use a neural network like a recurrent neural network or an LSTM model and you try to generate what? Context vector out of a given input sequence. I gave you this example also. Suppose if you are going for machine translation and I say, hi, I am Priyanka. So this encoder will take that sequence, hi, I am Priyanka, will create a compressed meaning or context out of that input sequence and create a context vector. It is decoder's part to take that compressed context vector out of those input sequences and get me back the translated language, Namaste, main Priyanka hoon. Are you clear? So it is taking sequence of input, creating a compressed context vector at encoder end and then using that context vector at the decoder end and presenting you with another sequence of output. Are you clear? That's how sequence to sequence model worked. Okay. Now, what was the drawback? Of course, they were using recurrent neural networks. You had vanishing gradient descent problem. But also if you use LSTMs or GRU for longer corpuses of data, what you have again is again a vanishing gradient descent problem to hold that thing from starting to ending to get that context vector. Apart from that, you have this problem wherein there is no parallelism, whereas there is no concurrency. Every hidden state has to be, generated sequentially one after another. Yes or no? HT minus 1 is going and calculating HT and then say HT plus 1. Okay. So that sequential nature of calculation of hidden state, if the data becomes too long at the input end, then the computation cost is going to be increased, isn't it? So for that reason, into that sequence to sequence model, it was very important to implement another mechanism which could help you to attain concurrency, which could help you to get more speed, okay, and which could run or scan that input sequences parallelly also rather than sequentially. Also, I told you about bottleneck problem of sequence to sequence model. To remove that also, you require another mechanism. What was that mechanism? Attention mechanism. You remember I gave you one example. I have this entire 10 line of presentation onto the screen and you were not paying attention. The moment I say you pay the attention, would you have time in that span of time to go through every line sequentially? No. You will try to scan some important points which are highlighted onto the screen and then you will tell me a gist out of it. Probably you could be almost 70 to 80% there, but you will be able to escape the situation. Yes or no? So that is what attention mechanism is doing. Rather than going sequentially, it will try to figure out from the given input sequence what is supposed to be the next word that I must jump onto. Are you understanding? What should be the next token that it should jump onto? So attention mechanism brings that intelligence to your machine. So I taught you about different types of attention mechanisms the other day. Could you list out a few? Okay, self-attention, multi-headed attention, single-headed attention, additive attention. Yeah, so you remember, I'm glad. Okay, so what did we do in attention mechanism? Basically, there was a very small process that I explained you. Do you remember? Do you remember? What did we do? To calculate attention, first you have to understand what type of mechanism. See, try to understand this strategy. Of course, there is additive attention. Of course, there is multiplicative attention. Multiplicative attention mein you have dot product attention. Dot product mein there is a variant called scaled dot product. Okay, so that the values don't explode. Okay, so these are like actual formula that we try to calculate our attention scores with. So I told you there's always a process. You given an input sequence, you'll first try to figure out how are we applying that additive or multiplicative attention formula. How? Whether it is self-attention first you have to understand or it is a cross-attention you have to understand. Self-attention means it is going to verify one particular word and try to get its attention out of the same sentence. If it is cross-attention means you will take that particular word and try to get its attention, you know, similarity, how much important is the other word, you will query the other word which is present in some other sentence. So that is cross-attention. So first let us say here we are taking self-attention. So I should first decide it is self-attention. Then I should decide what type of mechanism, additive mechanism, dot product mechanism, scale dot product mechanism, etc. Okay. So suppose here we are taking scale dot product mechanism for an example. Okay. So I have now my strategy clear. So what is the process that you have to go for attention? That we will see. I'll explain you once again today with the help of a very small example so that you understand better. Now, what is the strategy behind this attention? To know which particular word to jump on to, which is more important. So that intelligence is given by attention mechanism to your machine. So actually in today's class, we are supposed to create an auto completion model using attention. Okay, so here I am calling auto completion. It's an extension of what we did the other day. The other day we did a word prediction, but here I am doing an auto completion. Auto completion means what? For a few words it will be extended and it will be able to complete a given sequence. Okay, so it's a sequence to sequence model or not? I am not generating one word, no. I am generating multiple words. So taking a sequence, generating another sequence to you. Understanding? Here I will be trying to use self-attention. Okay. Now, let's see the objective for today's exercise. The aim is to develop a model that could accurately predict and complete sequences of text or data given. An auto-completion model here will use scale dot product attention, which is designed to help predict and complete sentences or sequences of text. Okay. Think of it like a super smart predictive text feature on your phone. It's something like that. Okay, that we are going to build today. This is achieved by using scale dot product mechanism using self-attention. All of you pay attention to that last line. What it is telling? Scaled dot product mechanism using self-attention. So what is this scale dot product attention? Already I taught you in my last class. Now also I am giving you a brief overview out of it. Okay. So scaled dot product attention. So you all should know first that particular process that goes through. What do we require? First we require an input sequence. Second is we require pre-processing of that input sequence. Pre-processing may what you will do? Pre-processing of input sequence, what you will do? Tokenizing. You will convert that input sequence into unique tokens. Once you tokenize, what is the next step that you would do? Okay, tokenizing, lowercasing together at a time. Okay, and then word embeddings. So for that, what is the hyperparameter? You have to fix a particular size to your vector. Embedding size you have to select. Okay. Once that is done, your entire, all of the tokens that you would have generated would be converted into vectors. Are you clear? Once that is done, what are you supposed to do? How many of you remember QKV from our last class? So what is this query key value? Tell. All the tokens in the input. Yes, absolutely right. So here, because I am teaching you with respect to self-attention, the key components are query, key and value. Please remember that. Q, K, V. Query is for the current word that we are actually trying to find out what is the next word that should come. Okay, so it's like a target here, this particular thing. So this is your query, for which you are able to calculate attention weights of all the remaining sequences. Abhi these remaining sequences are of the same sentence or not, depends on whether it is self-attention mechanism that you are using or a cross-attention that you are using. So I am using your self-attention. So with the given input sequences only, I am trying to clarify what is the similarity between these two, how well they are connected with each other, what attention should I pay to the next word, I mean which word would be more connected to my query. Are you understanding? So that is query. What is key? Key will be all the tokens that you have generated throughout your input sequence. Key will hold all the tokens that you have generated as tokens from your input sequence. What about value? Value will be holding the true value of your keys. That is nothing but your vectors, word embeddings. Are you clear? So these three are your requirements when you are going for attention mechanism. Now to this particular, because self-attention that we are doing, we have to implement it using scaled dot product. So scaled dot product formula is this. Now important point guys, dot product means directly you would do say Q dot K transform, because both are matrices, one of them has to be transformed, right? So Q dot K transform. Normal dot product is query into key transform, but we are doing scaled dot product. Scaled dot product means you will be dividing that dot product of query and key with square root of dimension size of the key. That under root dk that you can see here is your scaling factor. Are you clear? Okay, so whatever be the dimension of your key, how long is would be your token, number of tokens, in that sense length of your tokens, then square root of that you will be dividing your dot product. it helps you to normalize it. The range of your dot product will not be exploded by that. Okay, computations will be easier. Okay, so that's why we are trying to divided by square root of dk. Now, does not end here. If you want to calculate attention mechanism, what it gives is a rough generalized logit. Okay, what you require is a value. When you multiply it value, it gives you a rough generalized logit. But what you require is in a certain range of probability. So probability ka range is from 0 to 1. To allot that particular range, you have to make sure when you multiply that dot product with its corresponding value, which is your vector, to get the answer in the form of a vector, you pass that through a softmax function. So this softmax function, you have already read softmax function when you have done activation functions. Okay. So softmax function will try to put it in the range of probability distribution, that is in the range of 0 to 1. Once it is done, you have calculated your attention using dot product mechanism. If it is self-attention, that query will be calculated with respect to the key. The key will be made out of the same sentence. Am I clear? Yeah? Makes sense? Do you want me to repeat this again? Okay. So figure it out. Okay. We are trying to calculate attention for a given sentence. Once we do one example, you will be clear. Okay. So we are trying to figure out attention for a given input sequence. Okay. So I am trying to calculate attention scores. You remember these two terms that I used yesterday, attention score and weight distribution. So attention score ke liye we used a mathematical function. Weight distribution ke liye we will use a distribution function. Yesterday I taught you this. Okay. Now, attention score, how am I grabbing here? What is the technique that I am using? Dot product, not just dot product, scaled dot product, because dot product sometimes gives to larger values as a result, which will not be easier for me to calculate, to go on with the computation. So I want to scale it. So mathematical function, what am I using? Scaled dot product. Between what and what? Between say a current word that I am trying to get attention, means after this word where should I go? Okay, understanding. So that particular word in my input sequence is my query. I have to figure out with my keys. Keys will be dependent on whether it is self-attention or it is cross-attention. Here we are using self-attention. So self-attention means all the tokens of the same input sequence you will take. Are you understanding? For an example, if I say, I am Priyanka, if I am giving, hi, I am Priyanka, I told you just now for language translation. First tokenize, hi, then I, then am, then Priyanka. And if I am doing self-attention, say, hi, what is my next particular word that I must jump on? So, hi is my query. Okay, hi is my query word. What am I supposed to calculate its connections with, its similarities, or to calculate attention to the next word with? First, hi to hi to I, hi to am, hi to Priyanka. So I am calculating attention scores of all the keys with respect to my query, so that I can jump onto the one which has got more. Clear? Yeah. So hi to hi to I, hi to am, hi to Priyanka. I calculate the attention scores. Clear enough, guys? How do I calculate? Scaled dot product. Suppose I am calculating for hi. So what is my query? Hi. Okay? And then it will calculate attention score with hi to hi to I, hi to am, hi to Priyanka. Okay? Based on what? This formula that I have just told. Key will be there. Hai na? So, query dot product with key. or query multiplied with key transform by, I am scaling, dimension, square root of 4, let's say, because 4 words were there, no? So, dimension of my key was 4, square root of 4. Huh? I have got that. This is attention score. But attention score are rough figures. You still cannot make out which one to go for, which is having another more important attention. For that you require proper distribution. Probabilistic distribution is what we choose generally, okay, because it fixes you into the range of 0 to 1. So, to these attention scores that you have calculated now, individually to every query, you will be applying your probabilistic distribution function. That is your softmax function. Once you do that, you get your attention weights. As simple as that. Process is simple, guys. Yeah. So, this is your scale dot product attention. Understand, self-attention is a general concept where each word or token in a sequence attends to every other word in the same sequence. Whereas, it also computes attention weights using scale dot product attention, but specifically in a setting where Q, K and V come from the same input sequence. Okay. Also, here I want to define one more type of attention. If you are using only single set of Q, K, V, then it is single headed attention. Okay. In larger volume of data, you will go for multi-headed attention where you will have multiple sets of Q, K and V. Clear enough, guys? Yeah. So, summary, scale dot product attention is a mathematical operation used within attention mechanisms. Self-attention is a specific use case where attention is applied within same input sequence using scale dot product. So, if I want to keep it very, very simple, I can also say that scale dot product attention is actually a mechanism, that is a mathematical operation that is used to calculate attention scores, whereas self-attention is how is that mechanism getting applied within a particular model to help it focus on different parts of same input sequence. Now, are you clear? Are you clear? Scale dot product attention, how we are using it through self-attention, and we will be using that in our model today. So, I think attention is now clear. I am thinking you have to respond. Yes? Yes or no? Once we see an example, it will be a very good yes from your mouth. See. Suppose I am taking this sentence. What is this sentence? We did the same sentence the other day. Huh? So, what is it? The cat sat on the mat. So, first my attention should go to say cat. After cat, where it should go? Where it should go? Sat or mat? That we are going to see. Okay. So, what are the steps? As I already told you, tokenization is the first step. So, the cat sat on the mat. All right. Assigning vectors, for simplicity, because we are doing manual calculations, I am assuming them to be a 3-dimensional vector, and we will use dot product attention and we will be using self-attention in it. So, let us assume these are your word embeddings I have randomly generated. For ease of calculation, only one precision. Okay. So, 0.1, 0.2, 0.3 and so on, all of them I have got my word embeddings. Clear everybody? Yeah. Now, first dot product calculation. Just have a look on how I have done this particular problem, all of you. So, I am taking dot product of both of them, trying to get the answer, and what I am getting here is 0.20. What I am calculating here, what is my query? Cat. I told you now, after cat, what we are supposed to do? Query is cat. So, first cat will try to get the attention scores for all the key tokens in the key, because it is self-attention, the same sequence. So, cat to the cat to cat, cat to sat, cat to on, cat to again, mat. Okay, now I am scaling this. Key vector dimension is 3. Okay, I have selected that as 3. So here 0.20 by under root 3, which is giving me some result. Okay, so after that I calculated for all. I did that for cat to the. Cat was query, the was key. And the subsequent values also we have taken and used the formula. Cat to cat 0.167. What was cat to the? 0.11. Huh? Cat to cat 0.167. Cat to sat 0.27 and so on till cat to mat. Okay. Now you got this attention score. You have to pass this attention score through distribution function to make sure you get attention weights. Weights are nothing but distributed values of attention score. Okay. So what do you do? Softmax function. Do you remember softmax function? What do you do inside a softmax function? What is the formula? Huh? E power? Huh? See, normally you take exponential of that say particular word for which I am calculating by sum of all. Sum of all. Right? So what you are doing here is exponentials you are trying to figure out for these scores. Take the first one and divide it with sum of all the exponentials. That would give me the softmax probabilistic distribution. So here you are seeing, I am quickly going through this. So for all these attention scores, you calculated the exponentials, you calculated sum of these exponentials, and for all these individual attention scores, you calculated the softmax values. So you get it as 0.16, 0.17, 0.19, 0.16. So that means for cat, you had it as 0.17. What is the next best attention weight that you have got? 0.19. What it is for? Sat. So the very next attention should go on sat, but not mat. Clear enough? So that's how attention mechanism works. Telling where to go as your next word. Need not go sequentially. Clear? So what is the conclusion of the softmax? These are the scaled attention weights for the token cat. The highest weight we got it for sat, indicating the strongest attention score. So the same mechanism we will try to build today in our model, which will help us to generate, suppose if I gave say 4 to 5 words in a sequence, it is going to generate say in our particular model we are generating next 20 words. So what next 20 words it should come? Using LSTM as well as attention mechanism we are going to see. Are you all clear? Yeah, attention is clear. How we calculate attention is clear. How the result is coming out of attention is clear. How concurrency is achieved clear. How time factor will be reduced if you implement attention inside an LSTM clear. So till the other exercise we did only LSTM. Today we will use LSTM along with attention to improve efficacy of a model, sequential model. Clear enough? Yeah. What makes you talk? Any doubt? Okay, so let's now quickly work towards building our model. Listen very carefully. You will be working on a similar type of data tomorrow. I'll tell you what is the difference also. Okay, once I start with the code, what would be the little changes in the exercises that you have to go for tomorrow. I'm not going to teach you. You'll have to extract that information from the code that I am teaching you today and implement that tomorrow. So, listen carefully. Now, okay, so let's quickly go through the code overview. The very first step, so we are having certain steps to be followed. You also will be following. Okay, so the first step comes is data preparation. As always, okay. So very first requirement for us is data preparation. wherein what you will be doing, you will be importing the necessary libraries that are needed, loading the data set, simple text cleaning, convert text to integer sequences. So these 4 steps you will be doing here in data preparation. After that, you will be using data loader. What is data loader and all, we will see. Okay, so data loader setup, yeah, data loader setup. So you will be using test and train split. You will be also using PyTorch data loader for better batch size usage of your input sequence. Also, you can implement shuffling for your training data to get, better result. Okay. Scale dot product attention class. So attention mechanism you will be trying to design over here using self attention, utilizing, scale dot product attention, mathematical calculation. So you will be calculating attention scores and weights, you will be applying softmax functions, all that things internally in that particular class. After that, you will implement, I am calling the model name as auto completion. So you will be implementing auto completion model wherein you will be able to write codes for your, you will be coding to design your embedding layer, LSTM layers, attention mechanism, linear transformation, which is your fully connected layer. Okay, then you will train your model by choosing suitable loss function, applying a suitable optimizer to it, and then training over some suitable number of epochs, which are again user specific, and then you will estimate the loss out of this particular model. Clear enough? Yeah. Next, at last, you are going to test this particular model by using some sample sentences. Are you clear? Okay. So, the very first step, we go for data preparation. In the data preparation, obviously, the very first thing is import your prerequisite libraries. Please close your laptops. Okay, import your prerequisite libraries. PyTorch importing, NN out of PyTorch I'll be importing, same as before. I'll be importing NumPy, I'll be importing optimizers, okay, and then I am importing train test split. See, today we are doing a whole together different type. The other day we did a different type. There are different ways of doing. I am choosing another method today. Okay. So, from sklearn package, we will be using test train data split, and then what else you have here? Something new? What is something new here? You have got torch utils.data, from that you are importing a data loader. So what is it? We will see. So as I told you, till NumPy it's okay. From sklearn you will split into training and testing. Torch.utils.data loader. What does it do? So this data loader will help you to efficiently load and batch the data during training. Mind you, we are working with large amount of text today. We are not working with 4 or 5 lines. You will see. So that is the reason you will have to pass your sequences as batches. So to work with batch processing properly, you require a data loader. Next, tensor data. Tensor data is also used to wrap the tensors into a data set which will make them compatible with data loader. So whenever you are using this data loader, you are supposed to use this tensor data set also, which will help you to wrap around your data and make it suitable to work with data loader. Clear enough? So these two are important. If you want, make a note of them. Okay. And then RE. Here it is like not necessary, depends. Like I can normally also go through and create my own tokens, or by using regular expressions module also, you can go for splitting of your words into tokens. It's up to you. It's just an optional that I have imported here, but I have not used it in my code. Okay. Now, How does this data loader work? We will see. So this data loader will wrap a particular data set and will provide you with batching. What is batching? For efficient training purpose, always a large amount of text whenever you are working with, it's always better you put it into batches and send it to the machine so that it trains properly. Otherwise, you will face your accuracy will not be that much. You know, when you send it in batches, accuracy is far better. Okay, so for better training purpose, you will have to use batching and then shuffling. So shuffling mein what do we do? Shuffling is basically done when we are doing with the training of the data. Okay, so what helps with shuffling? It will randomly rearrange the data to prevent any type of learning biases. Okay, for that reason you provide shuffling mechanism also. That also is done by using data loader. Parallel processing, because it works with multiple workers to parallelly load the data onto your machine. Automatic iteration, easy looping throughout the batches, because you are sending your entire data as batches. Easy looping will be done automatically using data loader. You don't have to write all those pieces of code. Are you clear? So that's how data loader works. Now, what is this tensor data set again? Tensor data set, it helps to organize the data when you are working with PyTorch model, makes it easier to batch, shuffle and sample the data. It works well along with data loader in order to streamline your entire training process. So both of them go hand in hand. Clear enough? Now, RE, suppose if you want to use later, okay. So RE, why you have to use? It helps for pattern matching. It will help you to find specific words or numbers or formats. RE is same as what we have been using in Python. Okay, so text cleaning, when you want to remove any unwanted characters or you want to find out a specific format for validation like an email address or a mobile number. Okay, so for all those things you will be using RE. Now, next step will be to load my data set. Here I am using a text data. It's a very big text. It's actually a book called Alice in Wonderland. Okay, okay. So I have uploaded the path onto it. Okay, Alice in Wonderland text, the book I have a text file as, and I uploaded onto my data set. Now I'm going to read that text file and store it in a variable called as data. Here you can see there is something called encoding. Okay, so what are we doing here? With open file path comma R, and then you are providing what encoding you are supposed to. So it will prevent the memory issues when you are using it in this way, if it is better. And then proper encoding. What is this encoding? It is like similar to your ASCII encoding. Okay, here what we are using is UTF-8 encoding in order to avoid errors with special characters. Okay, okay. Unicode transformation format it is called as, similar to ASCII. You know what is ASCII encoding, similar to that. But then if you want to avoid errors with some special characters, you go for this type of encoding which I am choosing here. So, next step is, once I did that, I want to read what is present inside my text that I have supplied. So it is going to read the entire content of that file and it will store it into a variable called data. Okay. Now, let me print the first 1000 characters of this data set that I have uploaded. So you can see it's something like this. Okay, as I told you, it's a book. So these are only first 1000 words that I am printing it for you. Clear enough? Lot of white spaces, lot of new lines, है ना? Okay. Now, so we require lot of text cleaning also for this particular data. So the next step we go for is cleaning of our text, wherein obviously what I am going to do, I'm going to generate tokens out of my given data. So let me go a bit by bit out of it. So the first basic text cleansing, I start by, defining a method for tokenizing, simple tokenizing. So you all know what I am doing here. What I am doing here, I am using split function to what? To generate tokens out of my sentences automatically and then convert that into lowercase to avoid any case sensitivity. So you can see here what we are doing. Data.lower.split converts the text to lowercase and splits it into words based on spaces. Simplest way of converting it into tokens. Once we have done that, storing it into tokenized text. Now, next is you require a vocabulary. Yes or no? You require a vocabulary. Vocabulary is what? What is vocabulary? It's a dictionary. It's a dictionary. It will hold your key as your word and your word vector as your, but यहाँ पर what we are doing here is, we are trying to first gather the positions. Okay? So here what we are doing is, word to index, create vocabulary and word to index mapping we are doing. So this step, we want to create word to index mapping. For that I have chosen here enumerate method. Okay, so now this creates dictionary where each unique word is mapped to a unique index. So in this code I will be working with indexes. Okay, fine. So every word has a unique index. This creates a dictionary where each unique word is mapped to a unique index. Very important point, all of you must note. This is text. So indexing here should start from 1. Why? Answer I will give you when I am teaching you the code. Remember this part. So here what I am doing? I am starting my indexing with 1. Can you see? I plus 1. Okay. So the indexing starts from 1, not 0, because usually indexing starts from 1 in text to pre-processing tags. That 0 we have to keep for padding. Okay. So I'll tell you where is this requirement. Right now you understand that our indexing starts from 1. Next. Obviously, word to index we generated. We are now creating index to word out of it in our next line. It will reverse this mapping to get you a dictionary which has got index to word mapping. Clear enough? Now, once you're done with that, see, I have implemented that part. Now, what is my vocabulary size of my code? What is vocabulary size? I calculated length of after converting that into index. How much is it? 4,950. So that many tokens were generated out of my input. Very big data, no? Yes or no? Till now we have not done that big data. Okay, we just used few sentences. So 4,950 is the size of my vocabulary. For an example, if I am printing vocabulary size, actually in that screenshot I could not be able to print the entire thing. Okay, it's an extension. You have 4,000 and how much? 950 word to indexes coming. Actually saw that. Okay, so just as a sample, you try to understand like came, got 1, mentioned 2, pineapple 3, all 4, etc. etc. Okay, now we will be converting text to integer sequences. That's a piece of code. I'll be breaking it down for you and explaining you everything. Okay. Now, in our previous exercise also, whenever I wanted to begin, it's a prediction. So you require contextual understanding of what you are giving as input. Yes or no? Yes or no? So what was the hyperparameter there? Context size. Sequence size. Yes, correct, you are there. Input sequence that we are giving, that much size we require. So here I am naming that as sequence length. Okay, so how much sequence length you are supposed to give as an input? We are giving here 5. Okay, sequence length 5. So now our aim is to what? We know it's a text data. We can convert it into vectors. That also can be used by any neural network. But then how do you train a model? How do you train a model? You require X and Y. You have to generate input and output pairs. That we have been doing in our previous exercise as well. Do you remember? Yeah? So the same thing here. I have to generate input-output pairs, for which here I have created two empty list input sequences and output labels. Here I am not working a lot with vectors because it is 4095 tokens. So I am better working here with indexes. Okay. Okay, so this is also one of the way to do it. Now, for I in this range of length of tokenized text minus sequence length, for why is this loop written? This particular loop iterates over those tokenized texts wherein it will create sequences of length 5 here that we have defined for the input and next word as the output. So the entire 4095, the list of tokens that you have generated, first 5 tokens, what is the next? 6th. Okay, like that, like how what we have been doing in our previous exercises, like that it slides and give you a list of input sequences and target sequence. Okay, immediately after 5, the next word would be your target. Are you clear? So like that you will be creating your input-output pairs. Do you remember this particular step that we did last time? Yeah. Now, the next is I am trying to use input sequences append. See, this is again a comprehension instruction that I have been giving over here. Okay. Now, what I am doing here in the first one, input sequences dot append word to index token for token in the tokenized text. So what is going to happen here is for each window of let's say 5 tokens here. 5 is nothing but your sequence length that you are working with. So for each window of this sequence length here, okay, this sequence length, tokenized text I is to I plus sequence length. So that's your sliding window for your context words. Okay, so you have got for each window of say 5 tokens that you have defined, it appends a list of indices of the words to the input sequences. So input sequences you kept it as an empty list. You will be tracking your 5 words coming across the tokens and you would be appending those indices. You already generated word to index. So those indices will be appended to that empty list here. So you will get input sequences here. Similarly, you will trace through the output. What should be the output? Immediately after 5 words will be your target, your output. So that next word, that is I plus sequence length, the next word will be added to your output label. The same strategy that what we have built our previous exercise, same way we are trying to do this also. Okay. Now, once you are done with that, important part, what are you doing? You are supposed to convert your input and output pairs as tensors. I gave a very good explanation the other day regarding why. Why you have to convert it to tensors? How many of you remember? Tell me. Why? The other day also we converted first to numpairs and then said that no, this has to be converted to tensors, PyTorch tensors. Why? Yes, wherein you can work with multi-dimensional arrays and it will reduce your computation time and GPU acceleration. Very good. And global Compatibility, excellent. So you all remember that, I'm so glad. Okay, so the next step after you have generated your input and output pairs would be to convert that into PyTorch tensors. So you already know this. Here, now important part guys, I am check the data type. The other day we did it with float and then long. Then here both are long. Why? You can ask me that question. Very good. Because here now we are not utilizing the vectors for further calculation. We know that it will be converted into vector internally, right? So the other day I showed you how it got converted. Now the vocabulary size is so huge that I don't want to, waste time in that part. So what I am doing, I am working with indices. So because if it is an index, it's an integer. So I am going to convert it into data type as long, right? Once you are done with that, try to print. Print your x dot shape and print your y dot shape. So what could you see? So what could you see? What are the output, what are the dimensions? What is the input shape? It's a tensor of size 26465 by comma 5. Why that 5 is coming? You defined a sequence length for your input. Are you clear how the dimensions got changed? Yeah, you are giving the sequence length there. That's how input dimension is different. Okay, indices with respect to 5 sequence length. What about output? Indexes. The next output index. Are you clear? So that's how you will be tracing the shape of your input and output pair. After that, obviously, try to take some of your data and use it for training. Remaining you can keep it for testing. So for that, sklearn package, and then from sklearn package, you will be using train test split, wherein it will be converting your data into xtrain, xtest, ytrain, ytest. So xtrain and xtest will have 5 tokens or 5 vectors internally along with their indexes. And what would be the output associated with each 5? 1. 1 index, the very next word as an output. Yeah. So what are you trying to give here is you are splitting your capital X, which is your all these set of input pairs. Y holded all the labels of your output. You are choosing test size as 0.2. What do you understand by that? 20% of your data you are reserving for testing. 80% of your data you will be using for training. What is that next one? Random state. Random state. Any idea? Reproducibility. So it's like a seed that you are giving. On every machine you will be generating the same output. Okay. So reproducibility, you will be using a random state. Here I have given it as 42. Okay. Once you are done with that, go create data loader. See, this is something new for you. Kindly pay attention. Okay. Go create a data loader object. Understanding? Change in the terminology. Go create a data loader object. Okay. Why? To efficiently handle batches in training and testing. How much big was your vocabulary size? 4095. You have to work with batches. So to work with that, you have to implement data loader here. Okay. So now batch size here, what I am giving? 64. So it is going to set up the number of samples per batch during my training and testing. I am choosing it to be 64. And then train data set, obviously you will be taking your train input sequences and output label for that same input sequences into train data set, and same will go with your test data set, but then you are sending it batch wise. The batch size is 64. Are you clear? So 64 samples at a time. Now, train loader, as I told, creates a data loader for the training data set. Important part here, guys, that you have to see the parameters that this data loader is taking. It is taking train data set, it is taking batch size, which we have given 64 here. Important part is here shuffle equal to true. What is the difference between data loader of train data set and test data set here? Shuffle. Very good, you make it up. So what is this shuffle? Shuffle equal to true, what does it do? What does shuffle equal to true do? Training data will be shuffled in every epoch. That means whenever shuffle is kept true there, training data I am keeping shuffle as true, not in testing data. So training data, when I keep shuffle as true, it will be shuffled in every epoch in order to improve your learning of the data, in order to make generalization more efficient. That is the reason for training you require shuffling. For testing, we are just testing it with a corresponding input. You do not require any sort of generalization process happening there. That is the reason for testing I did not choose any type of shuffling. For training I kept shuffling as true. Important point. Clear enough? Yeah. Now I am going to print this data set. What is this train data set when I am printing? It's completely different than what you have been seeing. See, data loader output, na? Once I have used data loader, I am trying to print. So what is it giving me? What is the output looks like? Object. So it is just the Python's way of printing location in the memory of tensor dataset object. It does not represent any issue. It just means that you have successfully created a tensor data set using data loader. Are you clear? Are you clear? So, what if I would like to see the content? How do I see? Now it is not displaying me the content. I want to see. So you can go ahead and check like this. You have to print, say, the first sample. Okay, after you have used data loader and created a data set out of it, directly it will not print for you. You have to use this strategy. So suppose if you want to print first sample. So train underscore data set of 1 will print you the first pair of input output. Check here, tensor, how many values are there inside that tensor? 5. So 5 is your sequence length that you define. So for those 5 sequences, 5 tokens, what is the output index? Both of them are now holding the type as tensor because you did that by using data loader. Are you clear? So what is the first input output pair? This is your input tensor and that is your output tensor. Suppose you want to know how many total number of samples have been generated using your data loader. Number of samples in the training data set are 21,172. So how efficiently has your data loader created it for you? You just specified sequence length, you just specified batch size and you passed away your training, training labels, training tokens and their subsequent index of output. It has generated you input-output pairs, that too of tensor type. And how many such? After shuffling on every epoch and all, that will also be done for generalization because you kept their shuffling true. That will happen throughout your training process. But how much is your number of samples right now? 21,172. What was your vocabulary size? 4,000 change. So out of your 4,000 change, say 950 something was there, 4,950, that much tokens, you are able to generate how many input-output pairs? 21,172 just for training, that out of 80% of your data. Are you clear? This is now complete different strategy today that we are following. A very simple thing you did the other day. Now you are working with a bigger corpus of data. You are seeing the beauty of this data loader, that how it is going to give you with input output pair. Clear enough, guys? Now, same happens with the test data set. Again, if you are printing directly, it will print you the object. If you want to check, then check your test data set in the similar way that you have done with your training data set. Okay, after you got your input into a proper format wherein you can actually start building your model, right? So from that entire book that you have given as a text file, you generated input-output pairs, splitted those input-output pairs for training and testing. So now those input-output pairs X and Y, X train, Y train, X test, Y test are good enough to be implemented on a model. Okay? So we are now trying to create some classes that are supposed to be utilized in our model. The first thing that we are going to create here is to define a scale dot product attention mechanism. So I am going to define a class here for the same. Now I am using an init method in it which has got parameter as hidden size. So what type of attention mechanism are we using here? I already told you. Self-attention. What is the mathematical mechanism? Scale dot product attention mechanism. So for self-attention, what do you require? Q, K, V. Query, key, value. Okay. So here, what are you going to give as an hidden size? Hidden size here will represent size of feature dimension in query, key, value. Query will be the word that you are trying to calculate attention with respect to every other word. If it is self-attention in the same given input sequence, key values will be holding and value is the subsequent word embedding out of it. Are you clear? Okay. Next is you will initialize your PyTorch neural network module using init method. Next, once you are done that, I am defining another method called as forward. What is the input that is, what are the parameters that this particular method is taking, guys? As I told, okay, because it is self-attention, you require Q, K and V, and in that you will be calculating attention scores. How you will calculate? Using scale dot product or dot product, anything. Okay, so here what we are doing, scaled dot product. Okay, so you require two things for scale dot product. One is dot product between query and key. Another is square root of dimension of key. Yes or no? So what I am going to do there, I am using there torch.matmul. So using that, you will be doing dot product of queries and transposed keys. Are you clear, guys? Formula, you will have to remember now. Okay, so you will be doing dot product of queries and transposed keys, and also you will be dividing it for scaling np.sqrt self.hidden size. So that hidden size will give me the size or dimension of my key, and I'll be doing that. Now this particular thing, if you don't scale it, it will give you only raw attention scores, which will be like rough logits. You will not be able to, it gives you a large amount of values, which will be difficult to process with. That's why you have to go for scaling compulsorily. So once you are calculated with attention score, directly we can use a? No. Attention score will be done through mathematical operation. What is the next one? Attention weights through distribution function. So what are you going to do here as a distribution function will apply? Softmax. So you remember now in the beginning of the class I told those steps. Okay. So convert all those raw attention scores into probabilistic distribution. For that, please pass the attention scores that are generated through softmax function. Ensure that each row of attention score sums to 1. That means it's a probabilistic distribution. In any case, softmax does that. it puts it into the range of 0 to 1. When you add up all the probabilities, it will make it as 1. Now, obviously, now take out the output. So here, what you are doing is, once you have calculated attention weight, you require true attention weight, for which you need values. Obviously, you multiply your attention using the final output. This step determines how much of each value has contributed to the final representation, isn't it? Q into K divided by under root dk, an entire thing to be multiplied with value and passed through softmax function will give you a proper attention value there. Are you clear? Right. Yes. This module takes in 3 tensors. Query, what we want to find relevant information for. Key, what is the reference for comparison. So key will determine whether it is a self-attention or a cross-attention. Okay. Value, actual data that will be weighted based on the attention scores. Output is weighted sum of values. And the attention score determine how much each value will contribute. So what are the possible improvements? This we are not using in our model, but I am just informing you in future. If you would like to implement any other model, what improvements could you make? So you can go for masking support. Attention also has something called as masking support to ignore certain tokens. When the tokens are very, very big, where you can ignore. So you can go for attention masking. You can, if suppose it is an overfitted model. After you have generated your model, you see there is overfitting. Then what you should do? You should go for regularization. So and for that, you have got attention mechanism which will be using NN dot dropout also. This is for future. I am not using this in my code right away. I am just explaining. In near future, when you will do your projects and you stop somewhere, this will be helpful. Next is, you can also go for multi-ed attention extension. Typically, you will be using it. In our subsequent classes, we will be showing you in transformer how you will be using multi-ed attention. Okay, where you will use multiple attention heads with different learned projections. Okay, so these are all some improvisations that you could do. Now, returning back to the code, we will try to define the model. Okay, what we will do is, let's take a break for 10 minutes and then we will start working with model. Clear enough? Okay, quickly be back in 10 minutes. What is our data set? What is our data set? Alice in Wonderland book. What is the format? What is the format? Tomorrow when you will be doing an exercise, you will be working on CSV file. Okay? So plan for that. Okay? So here I have chosen text file. You better prepare yourself for CSV file also. Okay? Now, we have taken this text file, we tried to open it, and then what? After that, pre-processing of the data. What did we do in pre-processing? What did we do in data pre-processing? Tokenization and lowercasing and word embedding, but here we have extracted what? We have done with indexes. Okay, word to index and index to word processing we did in the pre-processing part. Then was that data enough now to be trained to the model? No. So what we have to do? We have to generate input-output pairs throughout that sequences that we have given as sentences. So, what new thing that you have used in today's exercise? Data loader. What does a data loader do? Creates objects of data sets. You are creating data set in terms of batches, wherein you are able to provide batch size, and also you are creating objects of data sets out of it. You have to also pass the length of the sequence that you want to take to create those input-output pairs, so that, let's say, sequence length, if you are giving 5, the entire tokens or entire text will be parsed in such a way that first 5 tokens, the 6th one would be your output label. So like that, it will divide your data into a data set having input and output pairs. Yes or no? Once you are done with that, you will be using test train split. 80% of the data you will use for training, 20% you will use for testing. You are supposed to access that particular samples that are generated by using indexes. If you see the indexes, then only you will be able to check what samples are present. Let's say tensors are created of 5 size for input part, for the input sample, and tensor of only dimension 1 is created for your output label. Till there we have done. Okay. We defined a class for attention mechanism. Yes or no? So what is the type of attention mechanism you are using in your model? Why do you require scaling? To normalize the range of attention scores. Are you clear? So we are using scaled dot product attention mechanism and applying it through the technique of self-attention. What do you mean by that? Wherever you are calculating attention score for any query, the keys will be the list of the tokens from the same input sequence. That is self-attention. So you apply attention mechanism, you write a class for it. I am not applying, sorry. I am defining a class for self-attention using scaled dot product attention mechanism. Now I begin with defining my auto-completion model. So our auto-completion model that we want to design is a sequence-to-sequence model. Yes or no? Yeah, you are taking some, say, 5 words in a sequence. You are generating how many next words, that still you have to decide. Okay. Now, here you are using it along with attention to predict the next word in the text sequence. It combines embedding layer, LSTM, scaled dot product attention mechanism, and a fully connected layer. All these things will be present in your model. Let's go one by one. So here I am defining a class called auto completion model, wherein you can see the init function here taking following parameters. What are they? Size of your vocabulary. That means number of tokens that you have come across throughout your data. Embedding dimension. Embedding dimension means what is the dimensionality of the word embeddings that you want to take. Hidden size. Hidden size is number of units that you are taking in your LSTM that we are using here as a neural network. LSTM or your attention mechanism in that case. Once you pass on these parameters, what will happen? You start creating the embedding layer. What you are doing? You are calling an embedding layer. You are giving parameters as vocabulary size and embedding dimension. Here it will convert all the input word indices into dense vectors of size, embedding, dimension. So obviously you are now passing it as vector only, because now model has to start its calculations and trainings. So now requirement of vectors is there, so that the machine actually understands what word it is. Every word will have its own vector. So here that word vector is created by calling embedding layer. A very different story now, right? So you are calling an embedding layer, and so you are defining, an embedding layer wherein you are passing parameters as your vocabulary size, that is the total number of unique tokens that you have come across, and also you are fixing what should be the dimension of the vector. Automatically it is going to take up your vectors. So, is it a pre-trained vector model or not? Yes. Okay. So, helps the model learn meaningful representation of the words. After that, you define a LSTM layer here. Okay, once vectors you have got, you will be designing your what type of neural network model it is. So, the layer that I want to insert in my model is LSTM layer. You have already seen its parameters yesterday. Embedding dimension, hidden size, batch first equal to true. I explained you what is batch first equal to true. What does it do? Once you keep batch first equal to true, now the dimensions of your input and output tensors will change. It will have now batch first, followed it up with whatever it was having. Clear enough, guys? So, batch first equal to true, you will be giving embedding dimension, you will be giving hidden size dimension. Now, this will process your sequence word by word, and also it will be able to capture any sort of long-term dependencies because it has got an LSTM network inside it, and it will output what? Output of LSTM would be the hidden states. Okay. Now, why LSTM? Because it's suitable for sequential data. It is far better than RNN. All that thing you already know. It's better than RNN. It avoids vanishing gradient descent. For that reason, I've chosen here LSTM. Okay. Now, once you have created that, after that, what is happening? What is the output from LSTM? Hidden state. You will be utilizing that output to undergo attention mechanism. Okay. So, what is happening now? You are creating an attention layer here. So, in that you are using scaled dot attention. We defined this method now already. So, in that you are giving the parameter as hidden size. So, this LSTM output serves as query, key and also value. Okay. So, it helps the model focus on relevant words from previous time steps while generating the next word. So, you pass the output of LSTM to your attention here. Clear enough, guys? Once it is done, you will apply a linear transformation using a fully connected layer wherein it will map the attention output to a vector of your vocabulary size representing what are all the probabilities of the next word. Clear enough? Next. Obviously, for this again, I'll write a forward function. What should be the input? Input should be my X. X means training. What you are giving as train. Okay, training X. Training X means what is present? 5 sequence length is present. Huh? How many tokens in sequence? 5. Okay. So, that tensor we will be giving here, and you can see I have kept here embedded as embedding layer and output of LSTM as LSTM out comma underscore. I already told you why we are using underscore. Wherever in a code you don't want to take further multiple outputs out of an LSTM, thereby you have to give an underscore. So, here I will be taking only LSTM out, and the other part I am going to take it as an underscore. I mean cell state I don't want. I want only hidden state. Okay. So, embedded equal to self dot embedding converts the input token indices into embedding vector, which is the function of an embedding layer, and then LSTM out comma underscore self dot LSTM embedded means vectors from embedded layer will be passed as an input to your LSTM layer automatically here, and then what will be generated out of it? What will be generated? It processes these vectors from the embedding layer and generates you with the hidden state. Obviously, output of LSTMs are nothing but the hidden states. So, once you get that, you take those hidden states and pass that through attention mechanism. So, that's the process. Embedding, LSTM, attention. Okay. So, embedding, you are giving your X. You are trying to figure out vectors out of it. Okay. All these vectors will be given to LSTM. You are getting hidden states out of it. All these hidden states will be given to attention. what you will get is attention weights. Okay. So what you are getting here, attention out will be stored, wherein attention is going to take up inputs as LSTM out, and LSTM out. Okay, so all these three, query, key and value, will be the hidden states of your LSTM. Once you are done, you are passing on this output of LSTM. You will be taking only one of them, okay? That is your one of the output that you are going to take out of the attention. And last one, the last hidden state specifically, all the keys, all the values, but only one query. समझ में आ रहा? All the keys, all the values, but only one query. So attention out say you will get all these values, okay, but then when you are giving it to your fully connected layer, you only want to give one hidden state, the last hidden state. Okay, please try to recollect LSTM. It produces hidden states at every time step, but what is most crucial for us? The last one. So that we are taking here and giving it to the fully connected layer to predict our output. The last hidden state will be actually taken to predict our output. Yes or no? So same thing I am doing here, and I am trying to return my output. Extracts the last time steps attention output and passes it through the fully connected layer to produce your prediction for your next word, which is like a logit. Logit, okay. Now, once it is done, you will instantiate the model, you will define what last function you are taking and what optimizer you are taking. So, what it is? Look at that, vocabulary size. Vocabulary size is length of word to index plus 1, because we started from indexing 1. Okay, I told you, right? Text pre-processing, you always start your indexing from 1. So that's how here vocab size also length of word to index plus 1. Embedding dimension I am giving 100 means what? The vectors that will be generated for every token will have a length of 100. Dimension of my vector is 100. Embedding dimension is 100. I should also give hidden size as a parameter to my LSTM network. So I told you always it should be in the form of 2 power n, 32, 64, 128, 256. It has got large amount of tokens with it. Yes or no? So that's the reason I prefer here to choose 128 as my hidden size. And then I will be instantiating my model here and passing parameter as my vocab size. Embedding dimension is 100. Hidden size is 128. I have to fix my loss function here, wherein I am choosing cross entropy loss. Yeah, because you are choosing one word out of multiple. And then you will be, using a optimizer. I told you why Adam is a very preferred optimizer inside neural network, because of its adaptive momentum towards converging to the minimum value of your loss and giving you an optimized output. Here learning rate, I am preferring to keep it as 0.001. Again, learning rate is a hyperparameter, it is user dependent. Okay. So are you clear now? This is like a basic neural network that you have designed. Now, training the model, I'll take snippets and I'll explain. Now, training this particular model, you are writing a function there, train model. What all you are passing there? You are passing your model that you have created. You will pass train loader, val loader. Train loader, val loader, where it is coming? Train loader is coming from data loader. Training data set that you have created through data loader, you will pass as train loader. Testing data set that you have created through data loader, you will pass as val loader. Epochs will be again dependent on the user. It was a very big corpus, so I thought 100 epochs would give me a better model. So I prefer here to choose 100. You can take 50, run and check. If 100 is giving more improvement also, you can test. Okay, so here I have chosen it to be 100 for an example. Now, what we are doing here, for every epoch in the range of epochs, first initializing total loss as 0, you started training your model, you pass all the inputs and the labels. Inputs and the labels, what are they? Inputs are your training input sequences. 5 we chose, no? That 5 tensor we will take, and labels are nothing but that next word that we were predicting. That will be given to train loader, and your model will be trained on this particular training. You have set your loss function as criterion. Criterion mein we have given loss as what? Cross entropy loss. Okay, and the parameters will be outputs and its subsequent labels. Optimizer you will instantiate with 0 grad. Why 0 grad? For no accumulation of your gradient, to save your memory. Okay. Next, you will implement backward propagation, calculate losses, and update your weights and parameter at every step of the epoch, which is done by optimizer.step. Clear enough? Once you are done, you try calculating loss for every item. Okay, and then I am not printing normal loss here, I am trying to figure out average loss. So the average loss would be the total loss divided by length of my training data set. Average is that only, na? Total by number. So total loss by length of training set, and I am going to print this average loss for every epoch that goes on. Clear? Yeah? Shall we move ahead? Now, validation mein, we will evaluate this particular model. First, we are keeping, let's say, validation loss is 0, let's say initializing. And then here again, no grad. Why no grad? Because while you are calculating testing part, there is no need for you to have that backpropagation gradients to be calculated. So, no grad there. And for all these inputs and labels in the testing data set, val loader means your testing data set that you have created, you will get your output getting predicted for a given sequence of inputs. Now I want to train this particular model. I am calling it train_model, passing my model, passing my training data set, testing data set, and I am training this for about 100 epochs. Model building is clear enough, right? Now, shall we move ahead? Yeah. All right. You are noting that down? Did you note down the previous one? Please note this down. I can wait. I don't have an issue. Try to understand model building. We are trying to build model using different ways. I showed you one way in the previous class. Another way you saw it in while doing your hands-on. Today is another way. Tomorrow again you will work with something else. Because I told you, no, today I am working with the entire book text data. You will be working with some CSV data. There are different ways of doing it. Good for you for practicing. Are you done with this? Yeah. So you can see now, where do we begin? Yeah. What was the loss at the first epoch? 7.086. What was the loss? The end of the slide I could capture 32 epochs. What was it? Decreasing or not? That means the model is proper or not? Now at the end of 100th epoch, what is the loss? So 81 per week, it was 0.06. Go back. 32 pe kitna tha? It's coming. It's actually decreasing, decreasing, increasing, decreasing. That also you have to see. Epochs mein, it's very important. Choose suitable number of epochs. And take the number of epochs which are actually giving you more convergence. Okay. So here at say 100th epoch, what am I getting? 0.01. That is the least. Yes or no? Yes or no? Okay. So, now we will start writing a function for auto completion. Now we will check whether this model is actually giving correct outputs or not. Okay. So function for auto completion mein I am defining a function called complete text 1, wherein I am passing parameters as my model. Start text. Start text means what? Start text means what? What will be start text? Start text will be the 5 words that you will be giving to your model. Okay, na? So, what is this start text? The initial text that you want to give it as a prompt to generate the remaining part of your text. Okay. Then next parameter is word to index. Word to index, index to word we already did in our pre-processing part. The same thing that we are going to do. Take it and maximum length equal to 10. Maximum length equal to 10 means what? It will control how long will this auto generation take place. So after I give these 5 words, the next 10 words it is going to predict. There also this you can tweak 10, 5, 20 based on the type of model requirement that you have. Okay. So max length equal to 10 and you will evaluate your model. What you will do? Simply as you give your 5 words, machine will not understand. You have to pre-process that. What you will do? You will take that input, again tokenize. So that sample, that start text that you have taken from the user, you will again simple tokenize. We already written one function, no? Simple tokenize, will pass it through that. Again, we will, try to find up the index of each token in our word to index dictionary that we have already created. And then, if it is found, fair enough. If it is not found, important part guys. Do you remember I told length will start, indexing will start from Y. Whenever you give that start text, the prompting words, it will check through your dictionary if that word is available. If that word is available, fair enough, index will be printed. Otherwise, it will return a 0. So, 0 index if it is coming means what? That word is actually not there in your input sequence. So, you can call that as a padded token. That is the reason when we did our pre-processing, I told you to start indexing from 1. Got your reason? Yes or no? See, everything we are doing has got a reason. We have to understand that. You can process, you can write code in multiple ways. My way is different, your way can be different. But the logic remains the same, no? So that we need to capture. Okay. Now once that is done, so once you have completed your start text of 5 words, you will put that into completed text, and then for that underscore in the range, why do you use that underscore here? When you don't want to take any variable there, you can go for an underscore. So for that in this, so this was the thing. Looping for maximum length. That means what is the maximum length that you have treated here? 10. Okay. So 10 words, for 10 words it will be predicting the next word and printing those 10 words as sequence. Okay. So you will be looping this for 10 times. You will be generating 1 word at a time. So how many next words you want to generate will be dependent on this max length. Okay. Now here with torch.noGrad, because you are giving the result. This is inference period of your model. You don't require any sort of gradients here. Gradients are not calculated during inference to save memory and to save computation time. Okay. You will be taking output after you apply this token tensor to your model. Model will take this token tensor, which is nothing but list of indices of this current sequence that you have given to your model, and it will predict an output as your next word. So predicted output is nothing but your predicted index. So what is this happening like this here? Output dot argmax1 dot item. What it is doing? What is this doing? So outputs model here that you get, model ka output is what? Probability, no? Yes or no, guys? It's a probability. It is not index. Output, model output will be out of all these available words, which one is having highest attention? Attention ka output, what we were getting? Probability, no? We did not today softmax apply kare. Why did we do softmax? To get the probability. What next words ka all attention weights you got. That was in probabilistic distribution range, no? That was your output. What do you require now? You cannot print that probability, no? You will print that word. So out of all those that you have generated, probability distribution, you will extract the one which is having highest probability. First extract its index, and through that index you will map in the dictionary and generate the word. Okay, so that's what I am doing here through this particular sentence. Model's output is a probability distribution across the vocabulary. argmax1 will find the index with the highest probability, and then dot item will retrieve the index value of that word. As simple as that. Output is in probability distribution form. Apply argmax to take the word with highest probability, highest attention. Highest attention. List out the index of that particular word. Now you got index of that word that has to be displayed. What you will do now? You will do index to word mapping. Take that index which has got highest attention now in the output, map it to the word and put it as completed word. Sorry, predicted word. What will be completed text? Follow this loop for 10 steps because you wanted the 10 words to be predicted. 10 times next word will be predicted. Everything will be arranged in a sequence. That will be printed. Okay. So this predicted word will be now appended to this completed text. For this will be repeated for 10 times. And you will also update the token tensor to get the new word. One word is predicted, you have to change your token tensor so that it goes to the model and predict another word. Model is actually predicting one word at a time. You are doing it multiple times here. So you can predict n number of words in the sequence. You have to fix it like this. Are you clear enough? So here you will be including new word also by updating the token tensor like this, and then you will be returning the completed text. Fair enough? Fair enough? Yes or no? Now, once you are done with that, you will convert word to index to word for convenience in the prediction. Once it is done, testing. Okay? So in the texting, what did I do? Suddenly she came upon a. Acha, yahan pe na little improvisation. You as a user, we did that interactive testing part now. You can even put that. First check if the number of sentences are 5. If they are matching with your sequence length. If it is less, you have to ensure you give a value error. If it is more, you make sure you truncate and take only last 5. Okay, that also you can do in this model. I am not done here to maintain simplicity. I already taught you once, you can incorporate that also here. Here directly I am giving 5 words. Input 5 words. So I am giving here, suddenly she came upon a. So my final output will be, once I get that, I take that particular text and then I write my completed text. You can see, suddenly she came upon a little three-legged table, all made of solid glass. There was nothing on one listening. So upcoming next 10 words were printed. Fair enough? I did a very simple testing code. You can make it an interactive testing code also, which I already taught you in my previous class. I didn't go that much depth today for testing. Just simple application I have taken, you can do that. I have changed the text so many number of times and checked. It was clearly giving correct predictions. I verified it from my text file also. So this is how you will be able to predict output sequences given input sequences using attention mechanisms with LSTM. If I choose only LSTM, I will not get that much accuracy. Also, the computation time will be lot more. Because attention was involved, computation speed was quite high. Clear enough, guys? Okay. So I think exercise is clear enough. I will switch on the quiz for you. Answer that. Post that. Once I stop the quiz, then only you go. Because till I stop, when I am stopping, by that time you submit your quiz. Okay?